welcome to today's session. So, last lecture we were looking at polytropic processes and general applications of first law of thermodynamics. So, we will continue ahead with that today. Okay, so quick recap of the previous lecture's final discussion. We looked at the general polytropic process given by the relation. So, it is a family of curves, the PV space, such that P is proportional to 1 by V to the power alpha, where alpha is any real number. And we saw that for this general family of curves, the work done is given by the general formula. And the molar specific heat capacity is given by the general formula. Q is equal to NC delta T. One more thing we should keep in mind. For an adiabatic process, Q is 0, so therefore molar specific heat capacity is 0. So gamma being Cp by Cv, we also saw it is 1 plus 2 by F. So there's an inverse relation over here that F by 2 is equal to 1 upon gamma minus 1. Therefore, Cv can be written as R upon gamma minus 1, and Cp can be written as gamma R upon gamma minus 1. So these are two additional relations that are useful to keep in mind. Cp and Cv in terms of gamma. So this is called the adiabatic constant. Whereas alpha in general here is called the polytropic exponent. Okay, so moving on, let's look at an example of application of polytropic process. Okay, finish writing this down. Okay, okay, Durgesh, done. Right, so let's look at an example of a polytropic process. So we have a gas expanding. So an ideal monoatomic gas is expanded from an initial volume of 1 liter to a final volume of 4 liters through a slow process such that pressure is proportional to square root of volume during the process. Okay. If pressure at A is 1 atmosphere and temperature at A is 150 Kelvin, then first of all, find pressure at B, temperature at B. Secondly, calculate heat supplied, change in internal energy, and work done by the gas for the process AP. Okay, so just try out this question, people. You can use the direct formula of polytropic process, or you can just use the fundamentals of first law also. Yeah, Samar, Dhruv and Jagannath, your answers are correct. Very good. Anybody else got the first part? Yes, part's good. So you can see for the first part, we can just use the relation P is proportional to root V, means yeah. So pressure at B becomes 2 atmospheres. And once pressure at B, you know, is 2 atmospheres, you can use the relation that ideal gas equation. So temperature should become 8 times temperature at A, 1200 Kelvin. No, we'll use ideal gas equation also, na? Durgesh. Understanding, we'll use ideal gas equation because it's given to us that it's an ideal monoatomic gas. So not only that, we'll be also using the fact that degrees of freedom is 3. So CV is equal to 3 by 2R, or internal energy is equal to 3 by 2 nRT for the ideal gas. These equations we'll be using. Understood? Now this point is clear, Durgesh?
Yes, sir, I got it. I just had a doubt that for like to calculate P, we had to use equation of state or this formula.
See, we can use either of them, but then to find the pressure over here, no, we are given the volume at the point B, and what else we are given? The relation between pressure and volume. No?
Yeah.
So we have to make use of this.
Okay. Okay.
Okay.
Got it.
Now, for example, to find temperature, in this relation only we can substitute ideal gas equation. So
Hmm.
we could have done that also. Instead of using PV upon T is constant, in this relation itself, we could have made use of the fact that pressure is nRT divided by volume. So if that's proportional to root V, that means temperature is proportional to V to the power 3 by 2. That's another way of expressing. So then we could have used that to find the temperature also. Yeah, so
Yeah.
depending on how we want to use the equation. So,
Yes, sir, got it.
okay. Okay, Samarth and Parth, you are getting slightly different answers for the second part. So let me check. So for the second part, we can either use, obviously for delta U to their standard formula, because it is a state function. So we'll just use NF by 2R delta T, which we can write as, in this case, 3 by 2 NR TB minus TA. So that can be written as 3 by 2 times PBVB minus PAVA. Which I have understood. You are getting slightly different values because you have used slightly different values of 1 atmosphere pressure. That's fine. Both your answers are correct then. So this is becoming how much? This volume is 4 liters, 1 liter, 1 atmosphere, 2 atmospheres. Okay. Temperature of 150 Kelvin, temperature of 1200 Kelvin. Okay, so I'll use this value. 1 liter atmosphere is 101 joules. So internal energy is increasing by this factor. Eight minus one. Piyush, this term here is PB into VB, so that's 8 minus 1. The product of pressure and volume here is 2 atmospheres into 4 liters. You can also take this as approximately 100 joules, especially if it is given in the question to take 1 atmosphere as 10 raised power 5 newtons per meter square. Then we can take this as 100 also. So if we take this as 100, then this becomes approximately 1050. But more precisely, it is this much. So that's our delta U. Okay. Now for the path functions, we can either make use of the polytropic equation directly, or we can make use of fundamentals, that is calculate the work done by the integration method, PdV integration. So obviously, if you remember the polytropic equations, it's much easier to calculate it that way. It becomes a formula based question. Whereas if you don't remember the formula, then you can always stick to the fundamentals. So for W, we can either use formula. So P is proportional to V to the power half, which means PV to the power minus half is constant. So this is a polytropic process with alpha equal to minus half. So therefore W is equal to NR delta T upon 1 minus alpha. So that will become 2 by 3 NR delta T, or work done can be written as PBVB minus PAVA divided by 3 by 2. How we got alpha's value, na Jagannath? See, we are given this thing that P is proportional to square root of V. That means P is equal to some constant into V to the power half. So that means P upon V to the power half is equal to a constant, or PV to the power minus half is equal to a constant. Okay, understood, na Jagannath? Okay. Okay, so just now we had seen that PB/VB minus PA/VA is 8 minus 1 in liter atmosphere. So that will become 2 by 3 of 7 into 101 in joules. So the work done by the gas during this expansion is this much now.
Good.
Yeah, any doubt? Telling the value?
Yes, sir. 471.33.
471.33.
3, yes, sir.
Okay. Okay. Yeah. So that's done. Now once you have found these two, you don't even need a formula for Q, because Q you can just calculate as delta U plus W. So already know these two, so you can add them up and calculate. Okay. Or alternately, you also have the formula that C for polytropic process is Cv plus R upon 1 minus alpha. So that becomes 3 by 2 plus 2 by 3 R. So in this case, it becomes 13 by 6 R. So Q is equal to NC delta T. So 13 by 6 times NR delta T. That's another way we can calculate Q. Okay. This Q will come out to be 1531.83
0.83 joule.
joules. Correct. Okay, so this is the easiest way of handling this question. If you just apply the concept of polytropic process and use the direct formula of polytropic process. I'll also show you the fundamental method in just a moment, but you can note this down. So out of W and Q, you don't need to apply the formula for both. You can calculate just one of the two and then use ideal gas equation also. Yeah, Shikhar, I'll explain that method also. Okay, so hope this method of using the polytropic coefficient, this is clear. Okay. Now the other method is we can always calculate once we have got delta U by formula. So delta U we have to use this only. So we got this. Then for W we use fundamentals. It is integration of PdV. It is area under the curve. So for this path from here to here, we want to calculate this whole area. So So because it's an expansion, so the work done will be positive of this area. Yeah, just a moment, Jagannath, I'll take you there. Is it clear now, Jagannath?
Sir,
Yeah.
you've underlined ideal monoatomic gas, and I've
Ah,
written something like F3, and
okay.
then what is
Yeah.
that?
Degrees of freedom is 3, monoatomic gas. Okay.
Okay.
Because and CV's value is 3 by 2 R upon it. So that's why we use this formula that U is 3 by 2 nRT. So that is
So
the
what?
formula we use for delta U because it's a state function.
Okay. Thank you, sir.
Okay, na? Okay. Yeah. So that so anyway we'll use in whatever method we are using for work done. But otherwise, if we are not using the polytropic equation formula directly, then we'll have to make use of this equation given to us. So given that pressure is directly proportional to root V, so you can say pressure is some constant, let's say K into root V. Okay. So therefore work done, which is integration P dV, is that constant into root V integration dV from A to B. So it will become K into V to the power half plus 1, that is 3 by 2 divided by this, integrated from VA to VB. Okay. So
Sir,
V, yeah.
so your K is the Boltzmann constant or any other
No,
different
no, K
constant?
is just some constant. K is not
Okay,
Boltzmann constant. Okay.
okay,
So we'll write it as capital K. So K's
okay,
value we have to substitute now. Okay. So K is just some constant.
okay. We don't know the value.
हाँ we
It's
know
unknown.
but indirectly because see यहाँ पे
Okay,
मुझे pressure पता है ना 1 atmosphere है. So
okay,
K का value क्या आएगा? Now we know that PA is equal to K times root V. Okay. PB is equal to K times root VB.
yeah,
So now we
okay.
were given this. So K's value is actually 1 atmosphere
Hmm.
per liter to the power half.
Okay, okay.
So its value is unity, but in this strange kind of unit.
Yeah, okay, okay. Yes, sir. Understood. Yeah,
So that is a tricky thing in this actually. How we eliminate the value of K? We eliminate it from the given point that A and B's both the things are known. A is both pressure and volume is known. So from that we eliminate K. Okay, na?
okay. Yes, sir. Understood.
Okay, so this is 4 liters. This is 1 liter. So this becomes 2 by 3. Now we'll put this value of K here. Okay. So K's value was coming out how much? 1 atmosphere per liter to the power half. So K now into the limits. So that is 4 liter to the power 3 by 2 minus 1 liter to the power 3 by 2. So you'll see not only important are the values but the units also. So ये आ जाएगा मेरे पास 2 by 3 into 1 into 4 to the power 3 by 2, that's 8 minus 1 to the power 3 by 2. But now the unit will be liter to the power half into, sorry, atmosphere liter to the power minus half. That's this one's unit. This per into this one's unit, which is liter to the power 3 by 2. So this is in liter atmosphere. Okay. So I'm getting the same thing. 14 by 3 liter atmosphere. Or 14 by 3 into 101. That is the work done. So that will be whatever value we had got here. 14 by 3 into 471.33. Okay. So this is the, we can say this is the fundamental way of solving. And if we make use of polytropic equation directly, it is like we have used this integration for the derivation of polytropic equation only. Na? Polytropic mein what we did, PV to the power alpha is constant So in that we made use of this only, that work done, which is integration of PdV. In the sense we would have done this only. It is that's how we would have got this relation, that is nr delta t upon 1 minus alpha. ठीक है, so work done ऐसा आ गया, delta U is coming from formula so now from these two add, so Q comes out. Okay, now next thing, let us move on to the concept of cyclic processes. Okay, Jagannath. Yeah, Shikhar, just finish writing this, no problem. Okay, so let's move on. So cyclic process. Now again, it is something you are familiar from chemistry. Cyclic process, what do we call a cyclic process? Any process where the um, final state of the gas is equal to the original state. So the gas undergoes some kind of a thermodynamic process where it comes back to its original state after that exchange of heat and mechanical work. Through that process, if it comes back to the original state, so it could be any process, need not be any of the named processes. It could be like this, or it could be, yes, that will use, that's correct. Okay, cyclic integration of, so this could be like this, or it could also be a case where the cycle is clockwise, anti-clockwise. Could start from some point A and come back like this. This possibility is also there. But the important thing is that the PV graph is forming a closed loop. So any cyclic process, it is a thermodynamic process, that is exchange of heat and or work such that the final state of the gas equals to the initial state after the process of heat exchange and mechanical work done and all that. Okay. So basically, PV curve should be a closed loop. That is a condition for cyclic process. So obviously, because of this, now this implies that final internal energy is equal to initial internal energy, or delta U is zero, because this is a state function. Okay. So that means Q in a cycle, the net heat exchange in the cycle is equal to the net work done during the cycle. So these are the two important things about any cyclic process. Okay, and then we will see that depending on whether the cycle is clockwise or anti-clockwise, these quantities are positive or negative. Just make a quick note up to this point. So this is an
Sir,
example
what
of
have you written after PV curve?
what have I written after PV curve?
PV curve.
Yeah, closed loop written.
So close.
It's a closed cycle or closed loop. So the graph looks like a closed loop or a closed cycle. This is a clockwise PV graph. This is a counterclockwise or anti-clockwise. So this also has a significance. What is the meaning of clockwise and what is the meaning of anti-clockwise? We'll come to that in a moment. Yes, Piyush, very good, that's correct. Clockwise we will see means that Q and W are positive, and counterclockwise means that they will be negative. Okay, so now additionally, if the cycle is clockwise, we will see that Q cycle equals to W cycle is a positive quantity as we were just discussing. So that means heat is supplied to the gas. The net heat is supplied to the gas, and work is done by the gas. So that means the cycle ends up converting some heat supplied into work done by the gas. So it's like we are supplying heat. The external agent is supplying heat to the gas and extracting work out of the gas. So that's why this kind of cycle, it is called a heat engine cycle. The system performs like a heat engine. It converts heat into work. It converts heat energy into mechanical work. Okay. So for example, anything from an internal combustion engine to a steam engine to a nuclear power plant, etc. It does this kind of thing. It converts heat into mechanical work. Now I'll show you the logic of why clockwise means this also in just a moment. So if we have a clockwise cycle, but mind you, clockwise PV cycle. So the P graph should be the y-axis and the V graph should be the x-axis. Okay. So if we have a clockwise cycle, we can divide the cycle into two half cycles such that you can see now here that going from A to B, the work done will be this total positive area. This total area is A1. Okay. So you can see that work done for the cycle is work done from A to B plus work done from B to A. Now, because it's a clockwise cycle, you can see that this will be positive of that area A1. Whereas if we consider B to A, it's a compression. So it will be this area here, the area enclosed by the lower graph going from B to A. So this area, it will be with a negative sign. So if this green colored area is A2, that is the area enclosed by this graph, okay, from B to A, just this part. This area, this one is A2. Okay. So this is going to become minus of A2. So the net work done during the cycle is going to be, that is positive of area enclosed by the loop. This is the area enclosed by the loop, but it's going to be positive of that. Okay, so that's why W cycle is positive. That's the logic why you can see that in a cycle that looks clockwise, the PV cycle looking clockwise, the area is, I mean, the work done is positive of the area of the cycle. Yeah, I'll explain again. Just make a note of up to this point. I'll explain this thing again. Yeah, Piyush shall explain. Jagannath and Piyush shall explain to both of you this thing. See, B2A is a compression, na? So compression में work done by the gas क्या होता है? Negative होता है because dV is negative, ना? Okay, let me explain this point first. We'll come back to this. Yes, Saloni, you can, those who are having the practical exam today, you can leave early. Uh, After the next 10 minutes or so, we will not be doing anything new theory wise. We'll be doing some practice problems. So you can go through the recording and the notes later. And you should be able to follow. If you have any doubts, we can discuss in the next lecture also. I think one of the days we are also having a doubt session. So yeah, Jagannath, I'll go up, but I just want to explain one point first. Okay. So see, what happens is that if we have a process of expansion, for an expansion, okay, now just imagine during the expansion I'm going from this point at a volume V to this point at a volume V plus dV. Okay. So for this small displacement from here to here, what is that work done? It is P dV with a plus sign, no? Because P is of course absolute pressure, which is the pressure at this point. But here dV is positive because it is an expansion that is taking place. The gas is expanding. Okay. So the total work done from A to B, which is integration P dV, will become positive of area, no? Become positive of this total area. Understood the point now? So for example, if we have pressure versus volume graph where the gas is undergoing a linear curve like this, let's say pressure is equal to half of volume. Now, half is some kind of a constant. So that constant half is actually half atmosphere per liter. Dimensionally it is like that. Okay. So now if I want to calculate the work done going from a volume of 1 liter to a volume of 2 liters, let's say. So this work done, so you can see it will be a positive quantity now because VB is greater than VA. Okay. Whereas when I undergo a compression, whereas if I'm going through any process where this is what is happening. So now during a small part of this, the volume is changing from V to V minus dV. Okay. So during this part, the change in volume is minus dV. No? So the work done by the gas will become minus PD. Or in general, the work done by the gas will be PdV, but integrated from VB to VA. So because VA is less than VB, so what will happen? This will be a negative quantity. So this will be negative of this area. Okay. So Piyush and Jagannath, this point is clear now. That anytime we have an expansion, the work done is positive. Work done by the gas is positive. And anytime we have a compression, the work done by the gas is negative. Yes, Piyush, this point is clear, beta?
Yes, sir.
Okay. So now see, go back to this one and you will understand here that in the cyclic process, kaisa bhi cycle ho, whatever the shape of the cyclic process is, but as long as
So basically, wherever there is a compression, it is always negative. Wherever there is an expansion, it is always
yes,
positive.
at any compression point the work done is negative and at compression expansion point the work done is positive. So हम क्या करते हैं, for a cycle we will divide the cycle into two parts. One is the expansion part, one is the compression part. So in the expansion part, in this case, A to B is the expansion. Okay. So A to B is going to be positive of this area. If this area is A1, it's going to be positive of this area. But when we are coming back from B to A, now we are interested in this part of the cycle. Yes, Shikhar, that's fine. We will do that. So B to A में क्या हो रहा है? If this area is A2, so work done from B to A is becoming negative of that area. So now for the whole cycle, we have to do the algebraic sum of this now. So it is plus A1 minus A2. So it becomes positive of the area of the loop. Is the area enclosed. That is this area. This is the area enclosed by the loop. Yeah, Samarth, I will scroll up. Okay, but first of all, this concept is clear to all of you now, no?
Yes.
Piyush and Jagannath.
Yes, sir.
Okay, very good. Okay. Okay, so I'll just scroll up. You can note down this part. Now, while you're noting down, you can also visualize if the loop had been reverse of this, if it had been anti-clockwise, then A to B would have given us the positive of A2, and B to A would have given the negative of A1. So the algebraic sum of the work done would have come out to be negative of that loop's area, not positive. So that is the case where Q and W become negative if it is a anti-clockwise loop, whereas if it's a clockwise loop, it's positive. So if the cycle is clockwise, then it acts like a heat engine. Okay. Yes, Prachi, you can leave for the practicals. We'll only be doing questions after this today, so you can take down the questions and practice later. Okay, so I think this part is clear. Let's move on to the anti-clockwise type of cycles. So for a counterclockwise cycle, okay, this becomes a negative quantity. So Q net is negative, means that heat is extracted from the gas, not supplied. Okay, because heat supplied is negative. Because net heat supplied is negative, that means actually heat is extracted from the gas. And likewise, W net being negative implies that work is done on the gas. Okay, so this functions as this cycle, then it functions as a reverse heat engine cycle or a refrigeration cycle. So this is something that converts or work is done to extract heat. Mechanical work is done on the system, not by the system, okay, to extract heat. So for example, that is a job of a compressor. A compressor is a type of machinery which accomplishes this task of a refrigeration cycle.
Sir, in refrigerators, right?
Yeah, compressors are used in refrigerators, air
Yeah,
conditioners, all
yeah.
these. So उसमें क्या होता है? Electrical energy is first converted to mechanical energy, and that mechanical energy or mechanical work done is used by the system to extract heat from one chamber.
Okay, sir.
Yeah. Okay, so now the logic of this is very simple. Why counterclockwise cycle will give us you just need to divide the cycle into two parts, compression part and the expansion part. So you can see that this is the work done during the cycle, but this time the positive part will be small. So if this area is A1, or whatever, this area is A2, this part is plus of A2. And B2A, which is the larger area in terms of magnitude of area, but that is coming with a negative sign because it's a compression. So this total area is suppose A1 like before, but this time this is minus of A1. So this net work done becomes minus of A1 minus A2. So negative of the area enclosed. So that is the simple logic why this comes out to be a negative quantity. Okay, let's look at begin with a very simple example. So we have a triangular loop like this. Of course. So here the volume is, let us say, 2000 milliliters, and here the volume is, let's say, 5000 milliliters, and here the pressure is 1 into 10 raised by 5 pascals. So a sample of oxygen gas undergoes the cycle ABCA. Okay. Given that temperature at A is 200 kelvins. So first of all, find pressure at B, temperature at B, and also temperature at C. Okay. And then find the Q for the cycle. Also find for the process AB and delta U for the process AB. So this is a fairly simple question. Okay. Two of the processes are well-known processes for which you can use the formula. And the third process, the one which is the diagonal line AB, you don't know any direct formula, but it's a straight line, so it's very easy to calculate the path function. So use the fact that oxygen is diatomic gas in your formula, and of course use equation of state of the gas, PV equal to nRT, because oxygen is an ideal gas. Okay, people, let's verify the answers. Okay, now one thing you'll have to realize, the answer that you're giving, that is assuming that this line AB is passing through the origin. Okay. So there's a slight issue in the question actually, because the graph is not exactly showing that. But without that assumption, we cannot solve the problem. So just a minute. What we have to do here is that the graph should reflect that fact, that we can assume that the line AB passes through the origin. So the graph drawn should actually reflect that fact, that it's passing through the origin. Then only we can make the assumption that because otherwise how we'll find the pressure at the point B, na? You're understanding the fact, Durgesh? So you could have one case where there's a straight line like this. Okay. So this is y is equal to mx plus c. Okay. So here this equation has to be used. Okay. Whereas there's another kind of line which passes through the origin. So this line is y is equal to mx. So for this we can just use the relation that y1 upon x1 is equal to y2 upon x2. You understanding now? So here the graph does not give us the slope, no? So anyway, so this is like pressure is equal to some constant into volume. M is some slope. So then we can use this relation that pressure at B upon volume at B is equal to pressure at A upon volume at A. So pressure at B will come out to be 2.5 into 10 raised power 5 pascals. Once we got that, then temperature at B will be 2.5 square into 200 Kelvin. So that is 6.25 into 200. So 1250 Kelvin. Samar, what do you mean by can be done in any process? Well, see, the process AB is not one of the standard processes, no? But from the graph, we can see that it's a straight line passing through the origin. So we can see it's a process where P is directly proportional to V. Whereas if it was not passing through the origin, then we cannot say P is directly proportional to V. And then your pressure is equal to some slope into V plus some constant. Understanding the difference between the two things, yeah. Okay, so we have done this. Now about the point C, you can see that, or directly you can see Ca is isobaric. So volume at C divided by temperature at C should be equal to volume at A divided by temperature at A. So temperature at the point C will come out to be, okay, so 500 Kelvin. Okay, just note this down. Just note. Okay, so temperature at C is becoming 500 Kelvin because of that reason. This is also done. Okay. So clear so far? No? Okay, now Q for the cycle. Now this is the easiest part. Q for the cycle will be equal to work done for the cycle, which will be equal to positive of area enclosed, area of triangle ABC. Why positive? Because it's a clockwise loop. So we can just use the area formula, half of base, which is 300 milliliters, into height, which is 1.5 into 10 raised power 5 pascals. So this is what I am getting for the value of Q cycle. No, the height of the triangle, beta. The height of the triangle is this thing now. See, this is the height of the triangle. It is pressure at B minus pressure at A. This is 2.5. And this is the base. It's 300 milliliters. Okay. Why won't we? Because we are calculating W for the cycle, na beta. W for the cycle is WAB plus WBC plus WCA. Okay. So this is positive of the area of trapezium. This is 0, but this is negative of the area of rectangle. So we are left with just area of triangle. E to B, we take this trapezium. So always remember, in the cycle, it is the area of the area enclosed by the cycle, but that area comes with positive sign if it is clockwise cycle and negative sign if it is anti-clockwise cycle. Okay, so Q for the cycle we have got, it is coming out to be this thing. Okay. Now let's concentrate on the process AB alone. Yes, delta U will be the same for any process because it's a state function. So for delta U, you will use that formula. So the third part, we just concentrate on the process AB. Forget about the whole cycle. So we saw that volume here was 2000 milliliters. The pressure was 1 atmosphere or whatever, 1 into 10 raised per 5 pascals. Whereas this was 5000 ml. So this became 2.5 to 10 raised by 5 pascals. Okay. Here the temperature was, what was it? 200 kelvins. So work done from A to B is integration PdV. So that will become positive of that area, but area of trapezium. This area. So it is half into sum of parallel sides into perpendicular distance between them. Yes, that's correct. And delta UAB, we can just use the formula. So oxygen gas,
Three one two five.
yeah,
3125 joules.
3125. We just check. If it is coming 26.2625 joules. Just check the calculation.
Okay, हाँ sir, wrong.
Maybe you calculated Q. Q will be the sum of these two. That will be 312. So QAB, if you calculate, and that will come out to be
नहीं sir, वो भी नहीं होगा.
okay. That will be this much. Okay, now there is also one more trick that we can use here, that for the process AB, you can see pressure is directly proportional to volume. So PV to the power -1 is constant. There's a polytropic process with alpha equal to -1. So you can also use this. It is NR delta T divided by 1 minus -1. So work done is PBVB minus PAVA divided by 2. Let's see. You can also interpret AB as a polytropic process. Okay, so hope this question is clear. So just write this down and we will conclude with another question. This is another type of situation you should be careful about in thermodynamics. So given that temperature is directly proportional to 1 upon square root of volume for a slow process, for a monoatomic gas. Okay, so if the gas is expanded from volume of 1 liter to a volume of 4 liters, and pressure at A was 2 atmospheres, temperature at A was 200 Kelvin. Find Q from A to B. Just try out this question after you write down the earlier one. We'll discuss about this. Exactly, Durgesh. You have to do the question by the polytropic method only. That is the easiest way to do this question. So if you use the given condition along with the fact that we are dealing with an ideal gas, okay. So temperature is proportional to 1 by root V also means that pressure into volume, okay, upon NR is proportional to 1 by root V because PV is equal to NR. So we get pressure is proportional to V to the power minus 3 by 2 on this, or PV to the power 3 by 2 is constant. Okay, Parth, you calculated QAB directly. Let's check out. Okay, so this is a polytropic process with the value of alpha as 3 by 2. So the molar specific heat capacity will become CV plus R upon 1 minus alpha. So since it is monoatomic gas, so CV is 3 by 2R. So this becomes 3 by 2R plus R upon 1 minus 3 by 2. Yes, it's a very interesting process, which is why I brought this up actually, that C comes out to be minus R by 2. Okay, so what this means, this basically means that this. So it means that heat is extracted, but the temperature increases. So it means that for delta T to be positive, Q is negative. So how that can be the process? Okay, so remember that Q is equal to delta U plus W. Okay. So now if this is a positive quantity, but if this is a negative quantity, that means W is a very large negative quantity. So the work done on the gas is such a large. No, so here Q will be a negative quantity because the temperature is, Q will be a positive quantity because volume is increasing, so temperature will decrease. Okay. But even before we come to that, and let's understand why this is the case actually. Okay. So P is proportional to V to the power minus 3 by 2. So on the PV graph, that will look like a very sharply decreasing hyperbolic curve. Like this. Okay. So compared to that, the isotherms are like this. So for example, if we are going from E to B, you can see that WAB is negative. Work is done on the gas. Okay. But delta UAB is positive because temperature is rising. Okay. So QAB is going to be a negative quantity because C was negative. So that means heat is extracted from the gas. So basically the internal energy is increasing by such a large amount that heat is extracted from the gas and work is done on the gas. So its internal energy is increasing. Okay. So now going from a volume of, so actually what we are doing is going like this, from a volume of 1 liter to a volume of 4 liters. So from a temperature of, what was the initial temperature? From a temperature of 200 Kelvin and a pressure of 2 atmospheres. So temperature at B is 100 Kelvin. Okay. So that means pressure at B will become what? Temperature has become half and volume has become 4 times. So temperature will be 1/8, pressure will be 1/8. So 0.25 atmospheres. You can use this only, that PAVA quantity. Use this, or you can use the fact that this also. Okay. So QAV, you can just use the formula NC delta T. So okay. Okay, so hope this is clear, people. So this is a very odd kind of process which is not very intuitive, that temperature is increasing but heat is extracted from the gas, because the work done on the gas is so much. So basically what is happening here is delta U is Q minus W. Now this is a very large negative quantity. Okay. So even though this is negative, this is positive for delta T being positive. So very large amount of work is done on the gas and heat is extracted from it. So even though heat is extracted from it, its internal energy is increasing, because a very comparatively large amount of work is done on the gas, even as you're extracting heat from it. So its internal energy increases, so its temperature increases. Okay. So that is the intuitive explanation of how this is possible. All right, so with that we conclude today's session. So next lecture we will look at more examples of yeah, that's all right, Sumit. Okay, that's correct. Okay, so with this we will look at more examples in the next lecture of cyclic processes, moving on to heat engines, in particular Carnot engine. And with that we will complete. Tomorrow we'll be doing doubts. So first of all, we will look at the doubts from the MT7, which are pending for some time now, and then other doubts from first law of thermodynamics, portion before that, kinetic theory of gases, etc., or anything in mechanics. If doubts are remaining, you can discuss that also. Okay, so that's it for today's session, people. Wish you all the best.